your snacks. I don't know about you, but that rum cake is to die for. Yum. Yeah, it's a good thing they weren't big pieces of cake. So let's go ahead and take our seats and we'll get ready to continue our program.
Okay. All right, so we're gonna continue talking about broadcasting the future, and in that vein, we're gonna talk about transport, IP broadcasting, how IP broadcasting enables hybrid OTT and OTA data casting, and our two speakers that will be kind of guiding this conversation are Dr. Young Kwan Lim. He is a research engineer and principal at Samsung Electronics out of Richardson, Texas, and Mark Corll, SVP of Advanced Technology Development at Treveni Digital out of New York. I'd like to invite Dr. Lim to please come to the stage, and followed by Mark.
Thank you. I would have a kind of 15-minute introduction about what the standard actually define, and then Mark will have more fun time how actually he has been implementing it with the a lot of complaints to what the kind of standard guys just kind of doing paperwork without considering how actually it can be implemented. Yep. Okay. So this green version, big one. No. Yes. Okay. So the Atsc 3.0 transport layers, the group I'm chairing is, has a two keywords, management and protocols. That's the group actually who developed one of the kind of, most famous or most kind of, widely, most frequently updated standard in these days, A331, which you want to find it from the website or somewhere. So that has a kind of two keyword, as I mentioned, management and protocol. So that's the kind of intention of the, the scope of the that standard, which I will kind of provide some highlight. What has been done, specified is the kind of, managing and delivering of Atsc 3.0 services and associated metadata over both terrestrial broadcast channel, and if there is a kind of a need or chance or support, then broadband together. So you can understand here that there is a kind of very important concept here that it's about the media and metadata together, and then it's about broadcast network and broadband network together. So that's not some that's kind of totally new concept probably. Compared to the analog broadcasting, if you want to see. Okay, so let me a little bit introducing kind of why we having develop our standard in such a way, IP-based way. Starting from the kind of history of 1.0 standard in the new in the Atsc. So you might know that Atsc 1.0 standard transport layer. Is based on MPEG-2 TS, MPEG-2 transport stream. The reason why MPEG-2 transport stream has been selected, or the kind of feature of major feature of MPEG-2 TS stream compared to analog TV service would be several things here. One important thing is a program multiplexing. That means in a 6 megahertz spectrum bandwidth, or 8 megahertz spectrum bandwidth, depending on the countries, for analog TV, you can send more than one TV channels, right? So that multiplexing capabilities was very important, since whenever you go from analog to digital, people want to have more channels. That has been one of the kind of benefit of analog to digital transition. And the second thing was clock reference locking. So because the The analog case, everything is just kind of, into a single, let's say signal, analog signal. So you don't have to think about, how do you kind of, recover the signal and then use it for AV synchronization. But, in a digital system, the physical layer you have heard so far, 1.5 days and, some kind of hour ago, that delivers signal and then recover signal is just bits, right? It's not a kind of, waveform anymore. So you need to process the bits, and then, that bits needs some kind of, reference clock. So one of the important thing, MPEG-2TS has tried to provide is, reference of the clock and use that reference clock to synchronize the AV, right? So you may not have that kind of experience because you are kind of transiting, after all the digital services has been introduced. Even though I'm quite young, I've been, going through the the transition in 20 years ago, right? The kind of analog to digital transition in Korea. And, one of the shocking experience I have ever had at the first time, we tried, analog to digital transition was that there's no lip sync. So video and audio was out of sync for several, seconds, and then people were scratching head. Why? Right? Because that has never happened in an analog world, right? If you put AV synchronized signal to the whatever system you're using, that that kind of what you get at the TV is also synchronized together. But digital world, you put synchronized input stream, but whatever the kind of black boxes does, may sync out, and then whatever you recover at the TV is totally out of sync, right? So I mean that's quite important how to get the clock right, and then use a synchronization that based on that clock. That has been a very important kind of feature and matters of MPEG-2TS. And also kind of PSIP, I had a chat with, Adam Goldberg, when I come here that, another, great experience, we had at the first time we tried to digital transition was, all the kind of, wrong information there in PSIP. PSIP was very important information to understand how many channels in the kind of stream and how to recover all the different things to from the stream and so on. So you can here see that MPEG-2TS has been very specifically designed for Atsc or digital broadcasting to support such important features. And then later on, Atsc has been working on Atsc 2.0. And then that has started to consider different features or additional features on top of the kind of the features 1.0 has provided. So you can see here that some people like the physical layer guys only tries to improve the efficiency. You have seen that the single graph just kind of going up. But this transport layer guys, thinking of a whole lot of different things, right? So out of that multiplexing and synchronization, what people has tried to kind of achieve with 2.0 was that interactivity, personalization, and kind of audience measurement, and non-real-time delivery. That means that you don't have to consume right away whenever you receive, but you can store it somewhere and then use it for later. And also some integration of other interface than just kind of broadcast. And then they also have a kind of added new video codec supports. So 2.0 has not been really kind of implemented a lot in the market, but it plays a key role of going beyond just kind of multiplexing multiple AV in the single stream, but thinking about different use case or different application for their broadcast stream. And then that has somehow kind of resulted 3.0. So you may understand that 3.0 is totally different transport layer IP based than previous generation of Atsc, but that doesn't actually happen overnight. There has been a kind of history of work done in Atsc for 20 years, thinking about what should be done in a broadcast system and how that can be more digital media ecosystem friendly. And then finally that big decision has been made in the early days of 3.0 to use IP. right? So that, makes, broadcast more friendlier with, any other, media ecosystem, as, Madeline also point out. And also, not only just kind of IP, but there has been also a very important decision to take, ISO-BMF as a media file format, here, a little bit gray. Because it sounds like a little bit weird that it's based on file, not the stream, but that has been a kind of choice because everybody is using that one. If you kind of just watching Netflix or YouTube or whatever, they are all based on ISO-BMF file, right? So it may sound strange, but it's not a totally kind of new endeavor. And then kind of that's more kind of an industry-friendly approach to use ISO-based media file format-based content over IP delivery. And there has been some, there has been a kind of, EPG or, program guide, based on OMA, BCAST, ESG, and watermark, which has been a kind of solution to make sure that any kind of illegal use can be protected some way. Also, there has been also important decision to use UTC, universal clock based. So as I mentioned that in MPEG 2 system-based, transport layer design, we try to convey the clock over MPEG to TS, and then clock, can be recovered through the, that matter by the receiver. But, in 3.0 transport system rely on UTC. There might be various ways of, getting UTC or reference clock in this way. You can use a kind of physical layer, provide a signal time, or you can use a kind of any internet-based, clock as well. So that will be a kind of, replacement of, reference clock in 3.0. So, what has been done here, as I mentioned that, the ISO-based media file format will be used as a, format for the, content, and then IP will be used as a delivery protocol. Then it doesn't really kind of, let's say, just put, happen in a way that just put IP, put, ISO-BMS FF file over IP. There must be some layer in between to make it, streamable, right? As I mentioned that, ISO-BMF file is a file storage, and then it cannot just kind of go, it cannot be, streamed right away. So there must be a kind of layer in between playing some important role. So one thing here is, as a green, is the kind of delivery encapsulation ISO-BMF file. So it's a file, it has a certain structure. So if you want to use it for streaming live, real-time services, then you need to somehow kind of, break down file into kind of, smaller pieces with certain purpose. That's the kind of layer, what, delivery, I'm sorry. Yeah. Yes, confusing. That's this layer, delivery encapsulation layer, is doing. And also there is another layer in between IP and this encapsulation layer is, application layer protocol. So Atsc has, chosen two different protocol for that, that purpose. So IP is a kind of general protocol. You can just kind of deliver whatever over IP. That doesn't mean that, and you cannot just deliver everything on top of it. You need to have some layer in between, like a glue layer in between the kind of this, like the kind of, file breakdown into multiple pieces, and then, IP layer. So kind of these two layers, has been developed by, Atsc, to make things, streamable in, various ways. Okay, so this is a kind of, stack diagram. As I mentioned that, over IP layer, there are kind of a 2-layer, 3 layers has been defined for kind of various purposes. You can see that, ISO-BMF is sitting on top of this layer. So Atsc has two different kind of protocol chosen. One is MMT, and the other one is LOUT. So they have a kind of different, natures and different design principles. I may not have a time to explain all the details, but they have different merits. So we have decided to have two different kind of application layer protocols to deliver, ISO-BMF file, and also they use a little bit different ways of fragmenting file into multiple parts. Which MMT use something called MPU. and route is relying on MPEG-, which is also very famous, format, protocol used by on OTT as well. And you can see that here the MPEG-, sitting on top of both broadcast pipeline and the broadband pipeline. So that has been one important choice that since MPEG-, has been used for kind of OTT as well for a lot. So maybe that could be a kind of good way to marry broadcast and broadband together, so that you can have a seamless service delivered through the broadcast channel or the broadband network, whatever preferred way, depending on your situation and so on. I don't think I can go over in details of this, but I can just give a little bit keyword explanation. So MPEG-, is a way to deliver iso-based media file format in multiple parts. That has been widely used by kind of OTT system. So what it does is to break down this iso-BMS file, which has certain structure, into multiple smaller part, which is called the segments, and then you deliver segments, different segments based on the kind of network situation, and also kind of device characteristics. So you may haven't heard about adaptive bitrate delivery. That has been a kind of an important concept widely used by OTT world or internet streaming world, which has been kind of just implemented through the MPEG-. So as I mentioned that Atsc has two different application layer protocol. One of them is allowed, which is called real-time object delivery over unidirectional transport. So there is an important keyword here that it's a kind of object-based delivery. So you can consider the each of this segment. Segment here as an individual object, so that you can deliver the individual object, but it's not like just kind of let's say downloading, as kind of considering real-time nature. So you can just kind of consume it continuously without waiting for a lot of time for getting down the kind of object. And also it's assumes a unidirectional transport, which is a broadcast in most of the cases. So this has been particularly designed for the purpose of delivering those dash segment over broadcast network. So this has been a kind of very important features, and some of the features may be kind of implemented by Mark about the NRT or data casting delivery as well. MMT is another protocol has been chosen for Atsc 3.0. It has been also kind of designed to provide more seamless and low latency delivery of media to the clients. So this has been designed that with very sophisticated buffer motor based control, and also it support a kind of UTC based delivery and jitter remover and so on. So a little bit of different focus, and then but still kind of focusing on the delivery of segmented iso-based media file format to the client with a unidirectional single delivery. I think that's end of my presentation. Then it's time for Mark, and then I will come back for the last slide for summary.
Thanks, Young. I will point out that Young is this year's Bernard J. Lechner Award winner for contribution to ATSC. I will also point out that there are many people in the room from ATSC that have won that same award. There's a lot of us in the room. Well, but the point is that there's a lot of people here that know this standard inside and out, and in fact wrote most of the standard. So, or at least contributed heavily to the standard. And so if you have questions, you have the right people in the room to ask those questions of, so we can answer those questions. I'm not very good at the phi layer, so don't ask me those questions, but this part, and then the next session, which I'm also part of, I'm the chair of those committees. So I can tell you what we've been doing for the last 8 years. I think it's been 8. I lost count. I have no idea. Anyway, so I'm going to briefly talk about data casting. This is a large, broad topic. And the interesting thing about data casting is that really we were trying to figure out some of the attributes about data casting, but ATSC3 is really a multicasting standard. That's what it is. It's multicast. It's a unidirectional one-way broadcast. So broadcast, multicast, they're really the same thing. It's one-to-many. And what's really key about this is that the number of receivers doesn't impact the delivery. Like in a 5G case or in cases like that, the number of receivers actually matters. Like the number of receivers you actually have in the network matters. Things start to slow down the more receivers you had, and everybody's probably noticed that if you're in a venue with a lot of cell phones, sometimes that happens, or in emergency situations. But ATSC in a broadcast scenario, it's not like that. The more receivers you add, actually, the cheaper it is, amortized across those number of receivers to get data to them. Like every receiver, you're sending out a specific cost per bit. Each of those receivers, that bit cost starts to go down as the number of receivers is taking advantage of it. So, but the delivery is really based on 2 parameters, the bandwidth used and then the reception quality. So I'll talk about both of those because data casting, it's important that both of those are taken advantage of. And I know in the previous presentations about PHY, that's all that's about as well. So you choose the robustness, in other words, the quality of reception over the amount of bandwidth that's used, right? So those are your trade-offs. That's really your trade-off. But both of these impacts the cost to deliver the data. The amount of bits that you get over time is really where the money is. So some of the use cases that have come up, and again, data casting really is not about, and I'll talk about this in a little bit, but data casting is really about consumption and how the data is really consumed. Audio video is really data casting in the ATSC3 sense. And really it's about consumption. You're watching the audio video live. It's real time. Whereas most data casting applications, it's non-real time. It doesn't really necessarily matter how fast or how quickly the data gets there. Yeah, it does matter in some cases. But like, for example, a firmware download, it doesn't matter if it came down today, if it comes down 3 weeks from today, it's still a firmware download. So really, that's what the part of it is, the consumption model, and they're all generally different. So some of the examples that we talked about, and you'll as you talk to people here in the show, here in the sessions, you'll talk about education or e-learning. As I just mentioned, the firmware software download or distribution, primarily to automotive. That seems to be the big one that's driving a lot of, and the reason we had reason we went to Detroit to talk to the automakers. Emergency information, this is very key, and I know there's a talk or a session on that tomorrow. Some of the other things are billboard, digital signage support, and more importantly, first responders, safety management. We can talk about a little bit about what we're doing in North Carolina PBS with them to distribute to pagers, of all things. So there's a lot of different applications out there for data casting over ATSC3. So ATSC3, I'll just go into it a little bit in detail. You've heard about it from Young, you've heard about it from others. We really have the best-in-class reception. So that's key for the receivers. You don't need the antennas, the rooftop antennas. You can dial it in so that you can actually get a reasonable reception in a handheld device, for example. It's IP-based, so it supports all of the regular OSI network layers directly. One of the interesting things about that is that in your studio, in the past for digital broadcasting, there was a ton of equipment that was very purpose-built for multiplexing, moving data around, things of that nature. Now it's all just IP. Your IT department knows how to do it. You buy off-the-shelf routers, you do all that. Your developers know how to deal with IP. Most people in school right now deal with IP. They're being educated in IP. So finding developers that know about IP is a lot easier than finding somebody that knows about ASI, and you probably don't even know what ASI is, and that's the point. But everything in ATSC is files. So all the AV, as Young just pointed out, is ISO-BMFF files. The closed captioning is IMSC1, TTML files, as Madeline pointed out earlier. The signaling ESG is all XML documents. Interactivity, which we'll get to next, is HTML5, CSS, and JavaScript. It's all files. So data delivery is native to the standard. The standard was built to deliver data. So ATSC3 is data casting. So some of the benefits of ATSC3 are the better reception, fewer carousel repeats, and by carousel, often in datacasting, because of receiver technology, you tend to repeat the files over and over again until you can be sure that all the receivers are going to see it for one reason or another. They're either not on, they're not tuned to the service, whatever. But so you repeat the data until you're certain that most of the receivers are going to have it, and also less bandwidth is required for the ATSC datacasting scenario. So based on the fact that we had the PLP mod cods, which you've heard about for the last 2 days, we can actually dial down or dial in what you would expect the devices that you're targeting with the datacasting to need for reception. For example, if you're going to a handheld device or some mobile device, you would want to use a different mod cod than if you were using an on-the-wall or a stationary device, or a vehicle for that matter. So you would dial those in. There's more overall bandwidth with ATSC3, so you can actually take advantage of some of those features and decide which bits you're going to use for what. And there's really less overhead due to the native IP transport. So everything is IP again. So some of the optimizations that we've done, or at least have thought about, or in development, really we're trying to improve both bandwidth usage and reception in some respects at the same time. So really what we're trying to do is build a tool set. And the interesting thing is that every datacasting use case is different. And every datacasting use case really wants to apply one or more of these tools depending on what they need to do. And that's what makes it a little bit challenging, because almost every use case is its own sort of just developed environment. We have a bunch of tools that you can bring to bear, but every one of them we have to really design and try to understand how you're going to do it, because sometimes the consumption model is completely different. It's not just a website exposing things. It's a car taking something in and then using it somehow. So all of that has to be thought through. So one of the things we can do is move AV or audio video out of the way. But one of the ways to do that is increase the compression and reduce the resolution. So you can go from UHD to HD to SD. You can also change a variety of other parameters within the audio and video to make them look relatively the same. They're not visually impaired, but they actually are taking up less space. So there's a number of things you can do, and there's an audio session or an audio and video session tomorrow, and they'll talk a lot about that. And the other thing that's being done is statistical multiplexing, which cranks down the bandwidth to be using a very specific amount of data, and it's clipped to that. So basically it's moving those files around in a very certain way and packets around to make sure that only a certain amount of data is used at a certain time. And along with that is statistical or opportunistic data insertion, which is basically anytime there's sort of a gap or bandwidth available, the NRT data can be squeezed in, can be pushed into there to basically clip everything to a specific bandwidth that you want to use. So anything that's not being used, any space that's not being used is filled up with data. Of course, the real-time multicast take precedence over that non-real-time data for now, but that's really a business decision. If all of a sudden somebody's going to pay you a lot of money to put in data, then maybe that takes precedence over some of your less watched video channels. And it makes sure that the bandwidth on the PLP is not wasted, right? So all of it's always met that limit on the PLP. Some other things that are in the standard, ALFEC, it's a Raptor Q forward error correction system. You can actually send, there's a lot of parameters here, but it kind of works a little bit like the PLP forward error correction, and you can pick and choose how much data you want to send along. And what that allows you to do is repair the files. So if packets are dropped, it will repair the files that are landing at the receiver. So again, reducing the amount of times you have to carousel it, but it's also trading off because you have to send the FEC data, just like you do in the PLP. You have to send the FEC data. Well, that's more data, right? But it's repair data. So you may not have to go through the carousel multiple times. You can only do it once or twice, and you know that 95% of the receivers have gotten it because the FEC repaired the files. But you can use that in combination with the PLP FEC. So there's a lot of tools we can bring to bear. The other thing we can do is measure the reception. So if you have a return path, if the receiver is connected to the internet, you can actually get information about how well the files are being received and feed that back into the studio, and then perhaps only send the bits that you didn't get before. So we block up the files into pieces and send only parts of them. And if the majority of the receivers got this piece, we aren't going to send that again. We'll send other stuff, and that minimizes the amount of bandwidth being used. And the other thing we can do, and this is sort of out there, is to actually connect the PLP configuration to the feedback. So if you see receivers in the field that aren't being able to receive the data well, perhaps you need to adjust the mod code in real time. Now, this is a future thing. We don't know exactly what the receiver is going to do when we do that, but it's something that people are starting to look into now. And then finally, the intelligent receivers. So if the receivers are in fact hooked to the internet, they can go out and find the extra data. They can go back to the server and actually use a hybrid delivery model. Now, that's a cost thing. So again, there's some potential AI and machine learning type techniques here where the receiver can then decide which broadcast path is better, whether it's the broadcast path or the OTT path, depending on the cost. And that's on the next slide. Some of the things that are happening, or maybe it's the slide after this, but basically the next thing that we're working on is essentially a purpose-built end-to-end data casting application. So every application, as I meant, has a different use case. Generally every data casting application really needs to be a system that's designed from the bottom up to do what it needs to do. So some of the ones that I mentioned, that's exactly what happened. And so I won't call them proprietary, they're more custom, call it that. And we work on that. And there really are generally some private protocols if we need to adopt things. For example, that pager thing that I mentioned, it's purely just IP. We don't have any actual data. The data is captured in just the IP packets. We don't have any other overhead. We don't have route because we didn't need it. And so we can actually use specific type of data casting techniques. So the future, again, I'll come back to the data consumption model. What is the data being used for? How is it being consumed at the receiver? And really all the data casting applications aren't created equally. They're all different. And you really need to optimize the tools you bring to bear to make the data work, to make the delivery work. And then a plug for what Atsc is working on really right now is the broadcast core network. And that may be where all of the smarts rely in terms of how to deliver data. Because the core network can make a decision across not only the single broadcaster, but perhaps multiple broadcasters, and actually allow it to be delivered over multiple frequencies or over OTT or whatever the most preferred mechanism is. And as Young pointed out earlier, everything's based on IP. So the hybrid delivery is actually built into the system. Young.
Yeah. No, I mean, this is one of my most favorite slides. So I just don't want to miss the chance to explain this one. So, beauty of, using IP as a transport layer for Atsc 3.0 is that, you can hide the different, physical layer interface, below IP, right? So whenever you use a smartphone, you don't really care whether it's, connected to a kind of mobile network or the Wi-Fi, right? Because everything is just kind of hidden under IP, and then you don't see any difference. So that will be the same case for Atsc 3.0. If you plug in Atsc 3.0 to any devices, and then you start to push the IP packets, then receiver, the layer above, will not distinguish, between the broadcast pipe versus any other pipe. So then you are adding, if you are implementing, Atsc 3.0, then, you are adding another broadcast IP pipe to the device. So that's the kind of, core feature I hope you guys can remember, at least for this slide at the end of this seminar. Thank you. Any questions? No? Questions? Any questions?
You can always catch us afterwards.
I'm looking at this slide on IP perspective. At the bottom, Ethernet, Wi-Fi, 4G, and TV. They all have return path except for the ATSC.
Yep.
So maybe it's a little bit, I'm thinking about your management at the receiver level? Because you do it on a return path. How do you stay at the transport level and know what's happening?
Right. Yeah. So, broadcast doesn't have, return path. But if you have a device integrating, other part of kind of other type of, physical layer, as you mentioned, that it has a return path. So, broadcast can use any available, return path. Since, it's all IP based. So from the server, or the kind of return path server point of view, it will be also same, whether, you get it from, original data, you get it from the broadcast or Wi-Fi or whatever. Make sense?
I could try.
Yep. Yeah.
The other thing, well, two things. Really, there's a lot of information that's carried in the broadcast to tell you exactly that. You don't have to go to the internet to get the information. It's part of the signaling and announcement, and all of that information is carried in the broadcast. And so really the system, if it isn't connected to OTT, if the receiver isn't connected to OTT, it has enough information to do quite a bit. And in the next session, you'll see you can do almost anything that you can do on the internet with it, except get information back from the receiver if it's not connected. However, there are, as Young pointed out, and the next point is, there are devices that have, I'm going to say, all of those built in, and you can see one back there on the table. It has an LTE connection. You can put a SIM card into it. It can connect back to LTE. It has a Wi-Fi connection. It has a Wi-Fi hotspot, and it has a receiver for ATSC3. So those devices are being built, and people are starting to deploy them.
Are you considering using those third-party return paths to possibly create some form of two-way communication?
Yeah, of course. So in other words, the applications that are run, and that'll be the next session, which Madeline is going to introduce, the return path, it's the applications don't know where the data is coming from. Honestly, they're just running. They don't know. And if they can get a connection back, just like on your phone, if you don't have Wi-Fi or something, it has no idea how to get back, you're in airplane mode, you're stuck. But if you turn that on, you're good to go.
Anyone else?
All right, we have one more session for you for today. Now we're going to turn our attention to interactivity. And we're going to invite back to this stage Mark Correll from Triveni Digital, who is also the chair of the TG3S38 group on interactive systems, as well as Raj Patel from Yada Labs, representing Pearl TV, to talk a little bit about how this thing is being implemented in the field. One thing that I want to make sure is abundantly clear, because I get this question from time to time, which is from the consumers, do I need an internet connection in order to use ATSC 3.0? The answer is no, you do not need an internet connection to do ATSC 3.0. A normal one-way ticket, one-way broadcast works. If you do have an internet connection, you can get into some of these advanced features that you were asking about. So I have an internet connection now that gives me a return path, and now I can do perhaps some additional things. But if you want to watch TV and you want to see some basic interactivity, you want to take advantage of the features like Voice Boost and other things, you do not need an internet connection. However, if you do have an internet connection, this is the type of thing that you can do. So I will turn it over to Mark, who's going to talk about the nuts and bolts, and then to Raj, who's going to talk about some of the real-world examples that are out there in the United States market today, and potentially talk a little bit about what's going on in Europe as well. I know you've got some examples for there. So without further ado, we're running a little bit late. Mark, it's all yours. Thank you.
All right, back again. Okay, so I'll try to make this fast, but there's one thing you should take away from this presentation and generally the interactive environment for ATSC, and I think somebody said it the other day, is that ATSC3, the interactivity is basically a website. If you know how to develop JavaScript, HTML, CSS, you're a long way toward knowing how to develop this stuff. Now, it's not the same, and I'll talk about that a little bit. But what we tried to do with the interactive standard in S38 was try to really define an environment that allows broadcasters to enhance the consumer's user experience. So we want to be able to personalize content, establish an individual viewer relationship so that they knew to come to your site and they could get information there, and you could get information back from them. And that was really where the feedback part of it comes from. We wanted to harmonize the internet and TV viewing experience, and I can't stress that enough. The system really allows that. And really, and then the other one is to ease, and I mentioned this before with the IP, we really wanted to ease the broadcaster and the receiver manufacturer development burden. So if you can imagine, like the receivers now, for a lot of the interactive stuff, they have to build from the bottom up, they have to develop all that software. If we build it on something that's sort of a standard or an environment that they're already using or already working with, it makes the transition a lot easier. They don't have to develop an entire interactive environment. They don't have to do that. What they did was they basically put a browser on the TV. And I'm really, really minimizing how much work there went on there, but conceptually, that's what's happening. So just a bit about the standards, and all of this stuff is out on the ATSC3 site, or ATSC org site, and the link is down there if you really want to know it. But if you go to the atsc.org site, it's pretty easy to just go to standards and you can see all the ATSC3 standards. The point of this slide really is that interactivity is another core part of ATSC3. All of the standards, well, how many are there? It's a big portion of the standards are really focused and help support the interactive content of ATSC3. The primary two, and the one that S38, the chair of the, I'm the chair of the committee that runs these, is A344, which is the interactive content environment, and 338, which is the companion device. And many of you may not know, but there's actually protocols defined by ATSC that allow TVs to talk to cell phones and to interact with a cell phone in the home if there's a connection there, a physical connection, or a Wi-Fi connection, for example. So the interactive content, the key features, I'm going to focus mostly on the interactive content. I have a slide in here about 338, but mostly it's about interactive content. What we do is describe a conceptual application operating environment. So we tell people that are developing the applications how the environment works, and we describe it in terms of here's the user agent. And user agent is a very specific term that's used to talk about a browser by W3C. And I'm going to throw out a lot of terms that are really internet specific. So my apologies. HTML5, CSS, and JavaScript. And we really wanted to provide a seamless, secure delivery of interactive content from both broadcast and broadband. So every bit of content that goes out over the broadcast is signed. So all of the applications are signed so that when they reach the receiver, they can be verified to be correct and have not been modified. And everything that's brought in from the internet uses TLS, uses HTTPS. So if the receiver is told to go to a broadcaster app on the internet, it has to use HTTPS. And Adam can tell us all about that if you really want to know. And we wanted to provide a separate, unique context for each application on the presumption that if there are multiple broadcasters in an environment in a market, you want to keep their applications separate, both from a secure standpoint, but also from they just don't walk on each other standpoint. If somebody decide to use the same file names and they land in the same memory space and collide with each other, that's not a good thing. So we kept the context separate for each application. And the way we communicate, the application, the JavaScript communicates with the receiver is via a WebSocket API, which is essentially meaning that the receiver acts as a web server. Part and parcel, that's basically what's happening. But also, because of that, we enable distributed receiver architecture. So there's not many on the market yet, but that could come in the future. So here's a picture of the environment. I like pictures sometimes more than words. But you can see basically it's pretty simple. There's the internet. So you can do broadband downloads and you can do content requests from the internet if you're connected, of course, previous discussion. Notwithstanding, the NRT broadcast is at the bottom there. And so all the data is transmitted via NRT over the broadcast. Let's presume we don't have the internet. All the data is sent to an application context cache, which is just a cache area. That's the context. And it's served up by the receiver as a website. So when the application runs, there's a bit of signaling that says, okay, run this application that you have in your context right now, and it will just come up on the browser. And I'll explain a little bit more about how that works. But then once the application is running, it can communicate via the JavaScript calls to the WebSocket API, and it can receive notifications. So it can do things like hear that there's new signaling. It can do, and I'll show you a list shortly. There's actually a pretty extensive list of things that we can do with the application with the receiver. So some of the fundamental concepts in A344 in the interactive standard is the broadcast application. You'll hear that, the broadcaster application. That's what Raj works on. There's a number of other people that work on that. It's basically HTML5, including JavaScript and CSS. That's the thing that's running. The receiver supplies the W3C user agent, aka the browser, display and run the BA, if you will. And the BA is programmed as if it was running on a desktop browser, but not entirely, right? Because if you think about a television, it's usually a lean back experience as opposed to a lean forward. So you don't have a keyboard, you don't have a mouse, you're not mucking around with stuff like that. So the applications have to be designed in such a way that they look more like television user interfaces as opposed to a website, right? You can still do the website if you wanted to. You could put up all that stuff. You could make the person cursor around, maybe curse is the right word, move around on the display and select things, but that's usually not going to be very acceptable. So the receiver really is a web server. The broadcasters publish the web content, all that HTML5, the BA, as it were, in a secure signed NRT data stream. They land on the receiver. They make that content available via HTTP. The signaling tells the receiver to launch the particular startup, and off we go. Okay, so this is kind of the way you could think of this in layers. So the bottom layer is the video, and that video is just playing. That's your normal video. And on top of that is any graphics that the HTML5 decides to put up or the CSS decides to put up. And then that's composited by the receiver to create the display, which is the top layer. So the application, the things on the right-hand side is in the HTML5 document, you can change things in a normal document just as you would, draw pictures and load pictures and do things like that. But at the bottom there is actually the WebSocket API request. And what this one was actually doing, we can scale back the video. So we can move the video, position it on the screen, and actually cause it to be smaller, and then fit it within the graphics, which is what's on the right-hand side there. So this one's a little detailed, but basically what it's showing is that each of the app contexts are in different areas, in different memory areas, in different caches, and any given time, only one of them is served up to the broadcaster app. If the app knew the other addresses, it could figure it out, but usually it's just told, here's where this one is, and it's told that when it's launched. So that's really how we keep all the different memory spaces. So in that case, and the reason we call them caches, because you can imagine somebody flipping around the channels or flipping around the frequencies, and they had a broadcaster app running and a set of files there from one, they moved to the other one, now they get a bunch of more files, both of them are still in so if they flip back, that broadcaster app can restart again quickly without having to wait for the files to come down. And that's the idea behind the caching. It should not be confused with the caching that goes on in the browser, which may also be there. There may be two different things going on here. Really, the bottom part of this slide is really showing the receiver memory, not the browser memory. So here's a quick list of some of the API features, and this is not exhaustive. So there's a query, we can get the settings and the signaling from the receiver, so we can find out if closed captioning is on, that kind of thing. We can register for subscribe to receiver notifications. So if something changes in the signaling or if something changes in the settings of the receiver, we'll get notified of that and react appropriately. Other things we can do, we can change channels, we can change services. probably don't want to change channels, but we can actually change services from one service to another from the broadcaster app. So one can imagine that content is like if you had some content that was, you could show your local content from your particular broadcast, and you could move within those services depending on what the person wanted to see. You can select tracks, you can set the volume only for the broadcaster application, not the entire receiver. And you can request various content to be played. And as I said before, you can scale and position the video. The cache management, you can mark whether files are needed. You can download things in from the internet into the cache if you have a broadband connection. And you can actually select, in the broadcast, there's a mechanism that we added that allows us to define which bits of the NRT content that are coming down that are actually going to be used by the broadcaster application. And we can mark those files as appropriate. So you can imagine targeting people with different content, and the content is actually marked in such a way that the broadcaster app can ask, oh, I only want these files. I know I have a family watching, so I want these files, or I have a man watching who's interested in trucks, so I want to get these files, that kind of thing. And we have content recovery management, which is the watermarking that was described earlier. DRM key management, receiver media player management. So the receiver media player is actually the video rendering that's going on the receiver. And then content replacement, the dynamic ad insertion, is also done from the broadcaster application. So we have controls in there for determining when content will be replaced. Just a quick note on the companion device. There has to be an application that's loaded into whatever the device, and the companion device, basically the standard allows us to communicate between the companion device software running and the receiver. So you can actually have two applications, one on your phone, one on the receiver, talking to each other. And we've done little experiments where we've had content on the big screen that then talks to the phone, and you can make selections about what, so we did a game, a kid's game, where you could actually ask them questions, they could select, and then that would be fed back to the receiver and tallied up. Okay, Raj, for some.
So, Wagwan, everybody. I think that you've seen throughout today the technical aspects of underpinning how you transmit 3.0, the interactivity, and I think I pressed the wrong button. There you go. There you go. So the green one. So this is the fun bit. This is the bit where I'm able to show and demonstrate what the broadcasters have been doing with kind of interactivity. You know yourselves how you do audio, video, content, broadcasting to your audiences. So when we bring on kind of interactivity, it's our sort of mission to be able to exploit the different kinds of use cases every broadcaster wants to do in the kind of TV space. And a lot of the kind of interactivity and the APIs that Mark's been demonstrating, how do we exploit those sort of services? So we take the 344s, we bring an interactive kind of a layer on top, which allows you to speak with your customers. Today, you're just broadcasting content, and the only way you can do it is putting ticker tapes, messaging, call this number, and that's a one-way interactivity that you're doing currently. So now with the 344 and with the interactive runtimes, we're able to now engage customers and do something else. And as you've seen some of the demonstrations here, they're kind of helping you to show what we can do. But the key goal, I think, is increase the time people spend on the channel and on content. And then also, as we're broadcasters, there's revenue to generate in terms of maintaining the sort of status quo, maintaining content, and maintaining things that we're doing with the absence of, with the increase of mobile technology, different handset units. There's a lot of things that are out there now available for customers. So we want to make sure that we can retain customer audiences. So what does this mean? So Run 3 TV, was formed out from Pearl and Pearl Network and a consortium of the networks in the US. And that started to incubate all of the ideas that every broadcaster had. And we took those lessons learned also from Europe, and so from HBB TV and the way broadcasters approach how to do interactivity there. And we took the best lessons that we learned from that side, listened to the CE manufacturers, and tried to corral a lot of the broadcasters what they want to do. So we are running with the current deployments with the Pearl broadcasters here. So Hearst, PBS, Graham, Scripps, they're currently running these interactive apps now in the US. These are kind of examples. The first icon that you can see there is a vertical menu where we generated an ability for broadcasters to kind of skin and customize and generate the branding with very almost no development effort, but repurposing their current digital content. So they already had RSS feeds, they already had clips and things already available on their websites. And so we had, 10 boxes in the field. We had 1,000 boxes, we had 10,000 boxes. So it's growing. And with that, you don't want to necessarily invest lots of development effort to creating a special 3.0 application. So we built an app that allowed you to pull off the RS feeds, skin and design that, make it station specific, make it local specific, add a player to it so you can do watch your clips back with a player, and generate kind of a menu to see who's out there, right? To give you a way of saying, look at the numbers, look at the activity that people are looking at. One of the key features is that it starts to create a way where you can surface up your current programming coming up later on in the evening. Maybe you have some sponsorships that you're coming through, or you have long form versions of a particular episodic content that you're saying, if you click this link, you might see a little bit of preview. I'm sure there are the drama shows that everyone's watching that you want to see what's the next episode. So you can then see, are there people watching? Are they going to engage? Are they going to click through? And just look at the numbers and see what's out there. The bottom angle, we moved away from a menu that's coming in from the left-hand side, and we went down to an L-bar route. We kind of launched that in NAB this year, and this will come out later on in the year. And it allowed us to now make it a lot more graphically rich, but also being mindful of the connectivity story. So yes, there is links to do video content, and you need a two-way, but how does a customer know that it exists there in the first place? So a lot of the application comes over the air, over NRT. The menus can come over the NRT. So at the point when the user goes and clicks and starts to discover, oh, I want to watch that clip now, that's the point where we've done the call to action, say, oh, you now need to make connectivity. And connectivity is a big deal, I think, here in Jamaica. And I think that that's one of the things that we need to solve, is how that back channel works, what are the right kind of experiences we could offer, and try and match that with what consumers are ready for as well in the marketplace. But the technology allows us to do this, which is a fully interactive return path, to a lightweight version, to a pure OTA version. The standard doesn't prohibit any of that at all. It's just our capacity to think what we want to do with it and what interactive services we want to offer. Part of the sort of marketplace that we run is we kind of run this middle layer. It's a framework, essentially. And the reason why we want to do this is we had two objectives. The first objective is we didn't want to constrain broadcasters to a one template app model, right? That wasn't the point of it. The key thing was that, can we get a service going that took very little effort for every broadcaster to set their development teams to code up something, just to generate a feed and to put something out there to see who is engaging with it and seeing what the transmission is like, what the operations need to do, what do the receiver manufacturers need to support, to see that system. The second objective was to create a framework where you can take maybe your current CTV applications, your smart TV, you might have already your 6 for Experience application, and port them over into the framework. So all the things around what Mark has described around the low-level WebSocket thing, we've tried to create a level of abstraction, which means that you can focus more of the experience that you want to do rather than the kind of nuts and bolts. You know, I think the analogy might be there are standards that will describe how to do encoding, but do you go and build an encoder? No, you might license and buy someone else's encoder to do that job for you. And that's what we're kind of doing here is we're taking the heavy lifting out from the low level and also the integration across different CEs and get you to actually build services and apps on top of that. Part of that stack, this is how our technology kind of looks like. So you can see where the WebSocket client is interacting with the receiver. But what we're doing is we're building kind of common modules that everybody needs. Everybody needs a data tracker. Everybody needs, like, say, an ad tech to do pre-roll ads. Everyone needs a player. We don't design the player. We allow you, the broadcaster, to stylize the player bars and stuff. But that whole control over doing that, identity management, how do we do that across all broadcasters? So we're solving those kind of harder problems that everybody has in the same fashion. And that means that we can code once, and then we can provide optionality to broadcasters, whether they want to use Google Ad Tech, or they have a customer data platform, or they want to build their own in-house one that they're using. So we're giving broadcasters choice to pick their own vendors and their own suppliers. But we know that we have tested this across multiple receivers and across different kind of configurations. And so, again, we pre-integrated with IBM, with their weather application and with their feeds. We've done some work with Google Ads, MadHive, Freewheel, and these are a lot of these are linear addressable advertising, particularly for the US market. But what that's helped us to do is work out, well, in order to do that, we needed data, and then we need an ID, and then we need a household ID. But then we need to manage privacy. We need to manage terms and conditions. We need to manage. There's a lot of things that go around just the one feature that you want to try and launch. So we try and bring that out. And so we've created a common privacy policy that the broadcasters are using, because we're staying within the remit of governance, of tracking of data, but with permission-based and anonymized, and where the kind of the sort of almost the stakeholders to help manage that kind of process on behalf of broadcasters. So you don't want to have the pain for everyone else, and everyone is treated the same way. So as a quick run through, I mean, I would have loved to have brought out a little demonstration. We've got, I mean, a number of applications that different broadcasters have done different treatments with. People have done live TV, live streaming on the back of their channels. Some have done, pairing up of identity with a QR code on a mobile. So we're allowing broadcasters to really experiment with the platform. And I think picking up what Madeline was saying around some of the things we've done in Europe and HBBT, in Germany, when HBBTV started, we had every broadcaster doing their own applications. And that meant that every manufacturer were trying to test off-air applications. And you've got 10, 50 different kinds of applications to test. So these are the things that we found that hearing from the CEs is we'd like to speak to one or two people about applications. We want to help you to manage what the broadcasters want. And what the Pearl role, and particularly with Run 3, is to pick out those feature sets, and then we think about, okay, actually there's a missing part in the spec, and so we look at putting those in the spec. The spec comes out 6 months, a year later, comes another 18 months. So when we're thinking about ideation of ideas and things, we're trying to think that it's a 2-year before it comes out anywhere near a set-top box or a TV. Okay, so that's the sort of thing that we want to try and do is incubate ideas that if there's something not in the toolkit, then we can put it in the toolkit. We can make workarounds around that. But if there's something fundamental that's missing, we can put that into the standards. We feed that back into the stack. It comes back in the Run 3 framework, and it's available for you. So that means you guys don't have to start standardizing and thinking about what's the lower level thing, because there's someone else that's already thought about that same idea that we have. So I'd like to welcome any questions at all on the floor, and hopefully Mark can help to answer some of those as well. No questions. Did a good job then, I think. Right, thank you. And I'm around here anyway as well.
So you know when you see me, it means something fun is about ready to happen, right? We have made it through day 2. Thank you, everyone, for your kind and rapt attention today. Thank you for visiting our exhibitors. We have about an hour and 15 minutes to kind of chill out, relax, maybe get your fancies on. We're having the VIP dinner tonight. You will come back to the convention center beginning at 6:30 this evening. We are having a reception out in the piano bar. I know Jamaica is famous for rum, and I have assured that the bar is stocked full of it. In addition to my own personal favorite, some champagne. So 6:30 reception, come say hi, let's be social, let's network, and then we have a lovely dinner this evening followed by some really exciting entertainment. So dinner right next door. So we are going to be, once the reception is done in the piano bar, we will just come back into the mirror of this room, and it is looking glitzy and glamorous in there. So thank you, everyone. Take a minute to rest, and we'll see you in a little bit.